Okay, welcome back, everybody. So the second and last talk this afternoon is by Chris from Carnegie Mellon, who will tell us about canonical forms of oriented matroids.
Yeah, thank you for the introduction. Good to see many of you and new faces. So Thomas Lamb gave a talk yesterday with a rather broad overview of his program about matroidal amplitudes or matroidal amplituhedra, and mentioned a particular foundational aspect that's joint work with me, and the details or some more details of that I'll talk about today. So there will be a good chunk of the talk. So before I begin, let me recall a quote by a famous Kennedy that goes something like this. Ask not what your physics or what your math can do for your physics, but what physics can do for your math. I think it went something like that. So for me, the entry here was given these structures, for instance, what's called positive geometry or canonical forms, can I learn something combinatorial or geometric and so forth? So that was sort of the entry that I had, and will be more of the focus of the talk today. So let me begin by setting up some notations and going back to the very basics. So I presume for many of the physicists, this will be a review of the concept called positive geometries. For some of you, maybe you have not met positive geometry, so this will be an overview. So I begin with a variety, let's call X, defined over R, and let's assume it's geometrically irreducible, reduced. I say normal, but most of the time it'll be smooth and projective of crude dimension D. And inside this variety, real variety, in the real points, I have a semi-algebraic subset. Let's call this the non-negative part. So there's a choice of a semi-algebraic subset satisfying one somewhat mild condition that when I take the interior of this semi-algebraic subset, it's an oriented, full-dimensional real manifold. So there's a choice of also the orientation for that part. So the data given so far is variety defined over reals, and then a semi-algebraic region in here, whose interior is a manifold with orientation that's chosen. And to avoid other kind of pathological behaviors, often it's good to assume that if I take the closure of the interior, I get this thing back. Okay, anyways. So given such structure, a series of authors, including Arkani Hamed, Thomas Lamb, who's here. I think Thomas is not here. I think he's still recovering from cold. Oh, he's here. Oh, okay. All right. So, and considering various structures that arise in the study of amplituhedra leads to the following purely mathematical notion, which I'll define now, called the positive geometry. So we say that a pair, like so, X and the non-negative region inside, is a positive geometry if there is a unique, rational, non-zero, top degree differential form, which we'll denote as omega of the pair. And this is the form that I think in many of the talks we've been referring to as canonical forms. And it has the following recursive characterizing property. So in the dimension 0 case, there's not much we can do. There's the point, and then the non-negative region is the point. And the orientation, I can either say plus or minus. In that case, the form is according to the orientation of the point, plus or minus 1. So that's the base case. And then here is the recursive property that characterizes the rest, which is for higher dimensional cases, this form, the canonical form, whatever it is, should have simple poles or log poles, I think in the previous talk mentioned, along the codimension 1 boundary parts of the boundary of my non-negative region. So what do? I'm looking at the non-negative region, take out the interior, and consider the Zariski closure, not the real closure, the Zariski closure of that boundary. And in that boundary, I'll have a bunch of codimension 1 components. Like in this picture, I have this will be the real boundary, but then in the Zariski closure, there are many of these curves. And the condition is that first, the canonical form has simple poles along each of these boundaries and no other poles anywhere else. And most importantly, here is the recursive structure, which is that when I look at any of these boundary components, let's say C1 in this case, that inherits its own non-negative region by looking at the boundary of my original non-negative region. And it also inherits the orientation by being a boundary of a manifold with a boundary. And the statement is that that boundary with that boundary non-negative region is also a positive geometry with the property that if I take the residue of the canonical form, I get the canonical form of that boundary. So there's this recursive structure where if I want to test whether this picture defines for me a positive geometry, well, first I check whether my form has exactly simple poles along these curves. And when I take residue, by residue I mean, for instance, if I write C1 as locally defined by one equation F, then I can write this canonical form as something wedge df over F, since I have a simple pole along F, and the residue is just the part that's not the df over F. Okay? Or you can think of this as actually like doing the integral around that boundary divisor. But in any case, just algebraically, that's the description. I think I saw some question. Yeah.
So this form is unique or unique after we scale it?
So literally unique on the nose is the condition. So in particular, my variety X cannot have any holomorphic sections. Like if I did, I can just add whatever multiple holomorphic section I like. Still has these kind of properties. So in the definition, the fact that I want a non-zero unique such thing means on the nose, I can't even change it by a holomorphic form and so forth. Like on the nose, there is exactly one. Yeah. Okay. Although like in real life, a lot of times we are not careful about the orientation, so it's up to us. Yeah. But there's on the nose one. Okay. Okay, so that's the structure of a positive geometry. And this was introduced in the work that I mentioned by these three authors and further studied in several works, only 2 of which I've included here so far. And many nice varieties with some naturally occurring non-negative regions are positive geometries. So for instance, toric varieties, which are some things I really like, have a notion of non-negative region. And turns out with that, it is a positive geometry. In this case, what's called a log cotangent bundle of a toric variety is already trivial, so there's not much one can do. And turns out it's a positive geometry, so it's not too hard to check. Another one that's been in several of talks this week so far is that if I have a polytope, let's say P, inside a real vector space, considered as a subspace subspace in a projective space, then that also defines, or that is a positive geometry. Another one that I think we saw in the previous talk, although not mentioned explicitly in this way, is if I take a flag variety, G mod P, for instance, something like Grassmannian, I guess 2n was among the focus, or some part of the focus in the last talk, and look at the positive portion or non-negative portion. Those define a positive geometry. And another one that Thomas mentioned yesterday and also mentioned in some other talks was the moduli space of pointed rational stable curves. There are many regions that you can call to be non-negative in there, all symmetric by some permutation group action. But for all of those, they also define a positive geometry. And lastly, and possibly most importantly, but still a conjecture, is that the amplitudohedra is a positive geometry. So this, I think, as far as I know, is still an open question. And part of the reason behind defining positive geometry. Okay, any questions so far? So this was very brief outline of positive geometry and their structure.
Do you require the form to be non-zero, like positive to be zero, positive?
I do require the form to be non-zero, so no pseudo-positive geometries. Although one could work with pseudo-positive geometries, I guess. But let me just stick with non-zero.
Non-dimensional x greater than zero.
Let's see. Do I require that? I guess at least not from the definition. Yeah. Yeah, Oliver?
That depends, but positive geometries are built up in points,
Yeah, it's defined recursively with this, yeah, by definition with this recursive structure. So for one-dimensional things, well, I need a curve, but if it's not P1, it will have holomorphic forms, global holomorphic forms, so I need to be on P1, and then I'm just looking at line segments or unions of line segments. So for one dimension, yeah, we understand it. For bigger things, well, yeah. Now, okay.
With some positive geometries which are not often with positive part of the ball.
Oh, with positive part is not a ball. So you could also take unions in most scenarios. I mean, sometimes you have to be careful about orientations, but you could take unions, for instance. You'll take so you get a union of balls. There are some other weird kind of other funky looking positive geometries. I'll briefly mention it, yeah, during my talk today. Yeah. Okay. So given a positive geometry, by definition, I'm given a variety and a boundary, a codimension 1 boundary part. And if you're, say, birational geometry inclined, one of the first things you can ask, given any kind of pair like that, is whether there is what's called a log resolution of singularities. Or more precisely in this context, one can ask for something like this. So I'm given a positive geometry. Maybe the boundaries are looking pretty terrible, or they intersect very non-transversely at some complicated loci. Can I replace it by something smooth? In other words, is there another, given such positive geometry, is there another positive geometry that's birational to my original one, in the sense that the positive region goes to the positive region in a diffeomorphic manner, and the source things are as smooth as you'd like. So the variety itself is smooth, and the boundary is what's called simple normal crossing. In other words, all the boundaries are smooth and intersect with each other transversely. Not just pairwise transverse intersections, but for every like triple or quadruple, those intersect. One might demand that they intersect transversely. So that will be the most nice scenario. I mean, it's a major result in algebraic geometry that over characteristic 0, whenever I'm given a variety with a boundary, I can make such log resolution. Short answer for positive geometry is not always. And here's like a silly synthetic example. And you can take these 3 triangles arranged in this way, orient all of them the same way. Each of them are positive geometries. Turns out their union is also positive geometry. And here the 3 boundaries, or 3 of the 6 boundaries, are crossing in a bad manner at the origin. 3 lines through the origin. And whatever logs resolution of singularity one does, that modifies this point, will have to blow up that point. And as soon as you blow up that point, the best you get is a pseudo-positive geometry. So it's a somewhat synthetic example, but At least in full generality, the answer is unfortunately no. But in many, I guess, sort of natural scenarios, the answer is yes. So for toric varieties, well, you just take the toric resolution of singularities. For the polytope case, it's already somewhat interesting. And this is the work that I have with Sarah Browner, Lizzie Pratt. Lizzie is here, and Raluca Vlad, who's also here. And Raluca will actually give a short talk on this work that we called wonder topes, which is exactly the answer to whether such nice resolution of singularities exist in the polytope case. And if you would like to know more about such things, well, I certainly encourage you to attend her talk, I think on Thursday. And for instance, this picture includes the M0n bar picture. So M0n bar arises as a particular instance when you try to take these kind of resolutions. So it's not quite a polytope, but it has the face lattice structure of a polytope. And for these flag varieties, probably, but I don't actually know the answer. I'm pretty sure some of the audience member here might be able to answer this quite quickly. And lastly, for amplituhedra, if it is a positive geometry, will it have a nice resolution of singularities? No idea. Okay. So that's one part of the question one can ask, as given just the structure of these positive geometries, somewhat independent from the physics kind of motivation it had in the beginning, and it leads to some interesting objects. That includes other interesting spaces. Now, here's a second question one can ask given a positive geometry. So another feature of positive geometry is that it gives you a form. It hands you a differential form, which has simple poles along the boundary. In other words, it's a section of a log tangent or cotangent bundle. So given this form, I can consider it as an element in the cohomology, or more strictly speaking, DRAM cohomology of the complement of my variety with the boundary divisors. And yeah, let's take the complexification. Yeah. So yeah, if I don't, I guess in the polytope case, things will be not too interesting. Yeah, and this won't really make sense. Yeah, so let's take the complexification. So yeah, the question is, can I learn something about the cohomology of whatever variety is involved whenever I have a positive geometry? And the answer is, well, hopefully yes. And presumably one can run these kind of questions and thoughts for instance, this example of flag varieties. But today I will only focus on possibly the easiest case, which is the hyperplane arrangements, which has appeared already in many talks. So let me set up some notations. Oh, but before I do, any other questions? Yeah, so now we'll just focus on the regions, in other words, polytopes that come from hyperplane arrangements. Let me make an amendment here. So here, let's say complex. So the boundary is I look at the real part boundary, and then take the Zariski closure. So that's an algebraic variety, and then now I'm looking at complex. Oh, you'd like to zoom in more? Let me try if I can actually rotate this. Oh, nope, that's not what I wanted to do. Okay. Better? Okay, good, good. All right. Any other questions? Okay, so let's now focus on hyperplane arrangement. So let me set up some notations. So here is a matrix we'll call A, consisting of n columns. Let's call it A1 through AN. A real full rank matrix, n plus 1 by n. And to avoid some trivialities, let's say none of the columns were 0. Okay. And given such matrix, I mean, for each column, I can think of each column as a linear functional by taking the dot product. And I'll often think of them in that way. And given this data, I can consider the hyperplane arrangement, real hyperplane arrangements, where I'm looking at the hyperplanes normal to each of these column vectors. And furthermore, I can projectivize the whole picture. So instead of working in R to the D plus 1, working projected D projected space, and look at the projectivizations of each of these hyperplanes. And lastly, in terms of notation, the key thing is to look at the complement of these hyperplane arrangements. So you can look at the non-projectivized picture, where I just removed all these actual linear codimension 1 subspaces, or look at the projectivized picture. And to stay on the same page, let me do one example. So let's say those were my 4 columns. So I should have 4 hyperplanes in 3-dimensional space. And here's the picture. And once again, this is probably one of the pictures that only makes sense to the one who drew it. Frankly, it doesn't even quite make sense to me now. So the better way to keep track of this is to pick one additional vector to delegate it as a hyperplane at infinity in the projectivized picture. So I take one extra linear functional, look at the hyperplane normal to that, or the 0 set of that. And this projected space minus the infinity, that is another copy of the real space. And that reduces the dimension by 1. And in this picture, if I take the infinity to be, say, 1, 1, 1, this is the picture. Okay. Then I can understand. Okay, so these are some notations to set up. And one theorem that's quite well known in the theory of hyperplane arrangements is, how can I understand the cohomology of complexified picture of this hyperplane arrangement? So I look at the projective hyperplane arrangement complement over the complex points. So this is complexified now. And that cohomology ring has some dimension. And I'm looking at the top dimensional cohomology piece. And the statement that you can get by combining a result of Zaslavsky and Orlik-Solomon is that the bounded regions that you see, number of such is exactly equal to the dimension of the cohomology. And I mean, in a sense, this is like implicit, or this statement kind of arises in many different contexts in terms of these like critical points by Varchenko, where each critical point occurs exactly once in these bounded regions. And if you're a little bit confused, that in that kind of context, usually the answer is number of bounded regions equals to what's called the beta invariant of the matroid. Here, the confusion, I hope, is resolved by me saying that you have chosen a general hyperplane at infinity. And with that added, the numerology works out as clear. But if you have seen those things and if you possibly find it confusing, in any case, combining some well-known results, that's what it says. And this is a numerical result so far, but there's like an obvious thing to guess, given that I know that each of these regions, being a polytope, are positive geometries. So this is like the most kind of obvious thing to guess, which is, well, the canonical forms of these bounded regions, once I fixed a general hyperplane infinity to draw such picture, form a basis of the top degree homology. And for this realizable case, I can even give you a proof. Like, it's almost too easy. So, okay, in this case, I have 3 regions. Let's say I took a linear combination using coefficients C1, C2, C3. Now, I want to say that if such a linear combination is 0, then all those coefficients are 0. But the built-in feature of the positive geometry is that, for instance, if I take a residue along this, then I'll have two regions whose canonical forms now have coefficients C1 and C2. And if I say by induction know that those have to be independent, then those are 0 and so forth. Okay? So just by inducting, using the recursive property of canonical forms, you can essentially see, at least given the numerology, that this forms a basis. So at the very least, one can convince oneself very quickly that this should be true. And then the question then should be, can I make this into a non-realizable statement or purely combinatorial statement? Yeah? So I didn't think about this. Yeah, so there is a basis given for this in terms of non-broken circuits or NBC bases. And I think I just learned from Bern that someone also has like worked out how to express canonical forms of the regions in terms of NBC bases. Yeah, but I haven't thought it through. Yeah. I'll give you a different formulation that comes into the proof of one of the main theorems. Okay, so from the picture, it was somewhat obvious what to guess, and it was almost as easy to prove it, at least given the numerology. And then the question is, okay, can I make this into a purely combinatorial version? And for that, I'll need to introduce one object, which I think many of you might already know. Some of you may not, or some of you may appreciate a reminder. So we begin with an object called an oriented matroid. So what is it? Well, oriented matroid, which I'll denote as curly M, on a ground set, let's say a finite set labeled from 1 through n of rank R, which will be d plus 1, where d usually stands for dimension, is the following data. So one can specify what an oriented matroid is by saying that I'm specifying a map called a chirotope map that sends any R tuple of elements from my ground set E to either plus, minus, or 0. And it should be alternating in the sense that the ordering of the elements matter. If I flip them, you pick up a minus sign. If any of them are repeated, 0, and so forth. And they must satisfy certain signed basis exchange axiom. Instead of writing them in full, let me just write down maybe a quick example. For instance, when R equals maybe 2, if I have that chi of 1, 2, and let's see, 3, 4. If these are both pluses, let's say, then at least one of chi 1, 3, chi 2, 4 minus, and chi 1, 4, chi 2, 3. At least one of these two should be minus. So there is some sort of basic exchange that one requires that also takes into account signs, and it's purely combinatorial condition that one can write down, and that defines what an oriented matroid is. And one terminology is that a subset will say to be independent if it belongs to some sequence of elements where the chirotope is non-zero. So oriented matroids here, if we look at essentially the kind of prototypical example of oriented matroids, well, if I handed you a full rank matrix, you can look at the various signs of the maximal minors, and that defines for you these chirotope functions. And these are what one would call realizable oriented matroids. And in, say, physical contexts and in many scenarios, you would start with realizable matroids. But sometimes there are needs to look at general oriented matroids, which exist in the sense that there are many such matroids in this purely combinatorial defined way that is provably does not arise as looking at signs of maximal minors. And these oriented matroids, often you write down some kind of intuitive thing that you want to generalize for these oriented matroids, and they generalize easily, or they can behave like a really subtle monster. So, and it's hard to tell exactly when that will happen, and a priori it's not clear. Everything you write down for the realizable case will just simply generalize to the arbitrary oriented matrix case. But let me feature a few notions that actually do generalize quite easily, or quite nicely, at least. I don't know about easily. So the first statement requires the statement definition of the Orlik-Solomon algebra of a oriented matroid. You can define this for, in fact, any matroid, really. But let me just stick with oriented matroids here. So what do? You consider the exterior algebra over, you can take arbitrary commutative ring. So take exterior algebra with bases coming from the ground set, which we call E, modulo the ideal generated by taking the differential of E sub s, where S is a dependent set. So for instance, if we go back to this example, this is an exterior algebra generated on 4 elements, modulo 1 element, E1, 2, 3, 4. And I mean, E sub S, this is just a shorthand for, or let me just write action on this, like E1, 2, 3, just shorthand for E1, wedge E2, wedge E3. And this partial operator is what you expect, the usual differential operator. E1, E2 minus E1, 3 plus E1, 2, 3. Okay. So that's the Orlik-Solomon algebra. And often, actually, in our case also, it's useful to work with what's called the reduced Orlik-Solomon algebra, where you look at the kernel of this partial map on this Orlik-Solomon algebra as defined. And so all these combinatorics is really highlighted by the following theorem, which says that the cohomology ring, in the case I have an actual realization of my oriented matrix, so if I have a complex hyperplane arrangement complement, then the GM cohomology coincides with the cohomology. This part is actually just Grothendieck comparison, but in any case, these cohomologies are actually purely combinatorial, and the map is you send the D-log form of the linear functional that we had. So here, since we projectivize, these linear functionals are no longer actual functions, but their ratios are. So I take D-logs of those, and that, under this map, goes into the reduced Orlik-Solomon algebra to exactly that element. And under that map, there's an isomorphism. So the Orlik-Solomon theorem states that I can completely understand the cohomology ring as this Orlik-Solomon algebra. Sorry? Say again? So if I'm looking at the unprojectivized, if I'm looking at just the usual hyperplane arrangement without projectivizing, then it would land in the Orlik-Solomon algebra, and d log of I will just go to EI. Here I need to land in the projectivized one, and the ratio goes to differences. Yeah. Okay. So we have one element now set. So whatever this canonical form of an oriented matroid or a region in an oriented matroid, whatever that is, should be, it should land inside the Orlik-Solomon algebra, or more precisely, the reduced Orlik-Solomon algebra. And before I state the main theorem, I need a few more ingredients. So now what do I have? I have the notion of oriented matroids, purely combinatorial. I have the notion of differential forms in terms of the Ehrlich-Solomon algebra. So the last ingredient would be, how do I say, regions? And this is also well known in the oriented matroids context. And it's called what's called the topes of an oriented matroid. And let me only define it in the case where I have a realizable matroid, although one can define it for arbitrary oriented matroid. So what do? Let me have some example. Is, well, for each connected region, I pick a general point in the region and see what the sign is under the linear functionals. So for instance, in this picture, I have these linear functionals with these directions. So this quadrilateral will be a tope encoded by plus, 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 plus. This one gets plus, plus, minus, plus, and so forth. And this notion makes sense for arbitrary matroids. Probably for the experts, the quickest way of saying it would be that it is a maximal covector, which is a composition of the co-circuits. So you take the oriented matroid, take dual co-circuits and composition. Any case, one can define it. And I have one more ingredient, which is deletion contraction, and it is essentially as it says. So deletion, you could imagine it as, well, I'm just forgetting about one of the vectors or one of the column vectors. In other words, in the chirotope, now I'm looking at chirotope applied to R tuple of things, not from E, but E take away the element I'm deleting. Contraction is similar in that instead of just getting rid of that column vector, let's say I, you're projecting away from that column vector. Or combinatorially, one can define it as the chirotope of the contraction is defined by, well, you adjoin that element that you contracted at the end and take the original chirotope. If you are worried, which you should be, that I might be a loop or co-loop for experts, of course, some of these definitions don't work, but let me not get into the details of those. Okay. And contraction in the hyperplane arrangement picture corresponds to looking at restricting my hyperplane arrangement to a hyperplane. For instance, if I contract at 1, I have an arrangement of 3 points on that hyperplane, and so forth. So far, all these notions have a realizable counterpart. And other than this theorem, it was relatively easy to guess and prove if you want to actually prove that these deletion and contraction works and tope works and so forth. Now, let me mention as a warning, one of the features that don't just carry over from realizable picture to not necessarily realizable oriented matroids. So if one looks at what's called a space of single element extensions, so these are given a matroid, I can imagine all matroids with one extra element, let's say Q, such that if I delete the element Q, I get the same matroid back. Right? So these are all single element extensions of the original matroid. And in the realizable case, what are all single element extensions? Well, I'm just adding one more vector. So it's a sphere. The space of realizable single extensions of a realizable oriented matroid certainly is just a sphere. I'm just adding a vector, and I only care about the sign of what vector I'm adding and the direction, not the scaling. So that's a sphere. But in general, if I ask for the space of single element extensions of an oriented matroid by an oriented matroid that may not also be realizable, this was conjectured to be homotopy equivalent to a sphere for quite some time due to Bern, who's here, and Zelevinsky, and disproved by Gakulu and only recently. And the proof that the space of single extensions for arbitrary oriented matroids is not homotopy equivalent to a sphere is so far only probabilistic. We don't know how to actually even write down a single actual example that provably fails this property. So some things in oriented matroid world may or may not carry over easily from the realizable to non-realizable case. And this is probably one of the major things that one can look out for when trying to just generalize everything into the combinatorial law. Okay, before I state the main theorem, any questions? So this has been, I think for some of you, mostly a review. Some of you, maybe a good review of oriented matroids, but any questions? Okay, so let me now state the main theorem. And it's what one might expect from the realizable case. And one just has to be careful. So the statement is that there's a unique way to assign to each pair consisting of an oriented matroid and a tope inside an oriented matroid. So to each pair, there's a unique way to assign an element in the Orlik-Solomon algebra of that matroid with the following recursive property. And given the definition of positive geometry, there's not much guesswork to be done. There's only really one thing one can write down. So in the rank 1 case, some base case scenarios. And then if it has rank greater than 1, then one would like to say that if I look at residue along some boundary, then it has this recursive structure. And the right way to say it is that for any element, if I take residue, by which I mean if I have an element of the form E1, 2, 3, and I take residue along 1, then it just takes out the E1 part. So I get like E3s and so forth. So there's a notion of taking residues. And under that notion of residue, which is purely combinatorial, well, there's the recursive condition. So if I have a tope, which is a sign vector, like plus, 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 minus, plus, for instance, and if I'm looking at the ith entry, when I get rid of that entry, is it still a tope in the contraction? If yes, then I can talk about that tope in the contraction-oriented matroid. So that should have a canonical form if it exists, and 0 otherwise. So this is the recursive definition for positive geometries, just written in the language of oriented matrix. Yeah. So here there's no bounded yet. Yeah. Yeah. That's right. Yeah. Yeah. So far there's, yeah, technically like there's no like kind of orientation data in this at this point. Yeah. Or the extra hyperplane and infinity data at this point. And possibly, at least to me, a little more surprising thing is that this canonical element in the Orlik-Solomon algebra can be written as the summation of things that look like this, where one takes any triangulation, which I'll explain in a second, of the oriented matroid and sum up over the bases that come up in the triangulation. And a priori, it's not clear at all if I just wrote this down, that this is independent of the triangulation. And even in the realizable case, this takes a moment of reflection. And so let's do the realizable case. And this is, this picture is implicit, or actually explicit in the work of Philemon, although he didn't say anything about canonical forms. So here is our running example that gave us this arrangement of 4 hyperplanes or 4 lines in P2. And instead of writing the hyperplane arrangement picture, I have these normal vectors to the hyperplanes. So let me draw those. So I take, in some sense, the dual picture, and I can triangulate that. So however you want to generalize triangulation to oriented matroids from that picture, that is the notion of triangulation of oriented matroid. Although triangulation of oriented matroid is actually a rather subtle notion that takes quite a bit of care. And if you would like to go through the precise details, there's a great monograph by Paco Santos. But in the realizable case, that's what it looks like. And what does this picture tell me in terms of canonical forms and the regions? It's just saying this. So this polytope should give me this quadrilateral. And the canonical form of that is canonical form of this simplex minus the smaller triangle inside it. This simplex coming from one of the triangles, the other triangle coming from this other triangle. So in the realizable picture, it's like natural to write something like this down. And given Philemon's result that such triangulation always gives you an expression for your polytope or region in the hyperplane arrangement, that will be a proof in the realizable case. But if you try to run the same proof that is in Philemon's paper about expressing some region as a linear combination of these simplex looking regions, what the proof does is it needs some quantity, for instance, this region minus this region plus this region equals 0. So it needs quantity like that to stay constant as I vary this hyperplane at infinity. I mean, that's one of the key steps in the proof in the realizable case. And at this point, you should get quite worried. Because if I want to make this a non-realizable proof, I'm varying this hyperplane infinity, or this infinity vector, the additional vector I chose. So I'm traveling within the single extension space of my matroid. And as I gave a small warning, that can be quite complicated. That's somewhat of a subtle beast. So we don't really want to do that. So how do we actually prove this theorem? Well, as great combinatorics Rota once said, if you don't understand something, you can still prove it by induction. So we prove it by nested induction within an induction. So it's true, but it's interesting that, for instance, independence of the triangulation for this formula is not a priori just obvious, although in the realizable case, there is a proof that doesn't easily generalize to non-realizable. Yeah. Yeah, that's right. Yeah, so I wondered a little bit about that. And yeah, in the pseudo hyperplanes, I have this like kind of wiggles as I go from an actual like kind of line and then little wiggle. So like, can I just have these regions and then, well, I just work with those boundaries with wiggles as boundaries and make that to a positive geometry. But then those wiggles will be its own kind of curve with its own boundary, and I'm not quite sure exactly how to deal with those. Maybe there is a way to kind of deal with that, go around it. But yeah, I don't think I saw anything quite clean. Yeah, through that. Yeah. So if I have a triangulation, I get some sort of a I see. Like, how are all these related in some sense as I kind of move through this flip? I don't know exactly. Yeah. I don't have a good answer.
In yesterday's talk, Thomas was right, at least in the realizable case, was writing these forms as Laplace transforms. Basically, use some kind of lattice point counts, let's say integer Laplace transforms. So I'm kind of just like a weight, and we do this, taking this triangle minus this triangle, we excluding some part of the side of this quadrilateral.
Oh, was this canonical forms the one that were Laplace transforms?
So yesterday, when we express this form with Laplace transforms, like in realizable case, lattice points, counts of lattice points of polytopes. So you kind of could be worried not only about internal points of this, region, it could be related but also be of the boundary. So just like literally take this triangle minus little triangle, we will exclude part of the boundary of the quadrilateral, which is almost the same, but having a little problem.
Yeah, I'm not sure if the one that was expressed as a Laplace transform was the canonical form or some related like bilinear pairing that arises from that structure. Yeah, yeah, yeah. Sorry, I can't give a very good answer, but Thomas is here, thankfully. Okay, yeah. We're almost done as well, so you won't have to wait too long. Okay, so we now have a way of writing down in some canonical way for each tope, matroid, oriented matroid, an element in the Euler orthogonal algebra. And it has all these recursive structure that mirrors the positive geometry. And after proving this, it's not too hard to prove the non-realizable version of this statement that the boundary regions for the cohomology. Although, I mean, at least numerically, this is certainly not a new result, nor is it a very shocking result at all. But it gives you a nice clean basis for the Euler orthogonal algebra. And the statement is that if once I fix any general extension, then it makes sense in the oriented matroid sense what a bounded tope with respect to that additional sort of possibly non-realizable hyperplane at infinity is, can be stated this way. So the topes bounded with respect to that forms a basis of the top degree part of the Euler orthogonal algebra. And the way one proves this, you don't even need the numerical equality anymore. You write it down, and I showed you how to show linear independence already, at least in the realizable case, and I hope you bought it. And with a little bit more care, you can write the proof down for the oriented matrix case as well. And you can also show it's spanning. And you can just show that there is some careful kind of sign things that you need to do with the sign circuits of a given fixed general extension and so forth. But up to a careful bookkeeping, you can also show that it's spanning by showing some identities like this. So you can directly show that it's spanning and linearly independent over arbitrary commutative ring. So you get a nice basis of the Euler orthogonal algebra in that way. And there's a usual trick to go from the top part to all the degrees by doing what's called a truncation, which involves a choice of further general extensions, but you can push this idea to get a full basis for the entire orthogonal algebra. And in the realizable case, we found that this basis was also considered in a work by Yoshinaga. He calls it the chamber basis, since I have a basis element of this Euler orthogonal algebra for each chamber. And the context here is a real arrangement and then complexify. So everything here is the realizable picture. And the proof there really requires a careful analysis of what's called an affine Lefschetz hyperplane theorem, exactly in this context of what happens when I cut a hyperplane arrangement complement one more time and how the cohomology changes. And one could show a basis going through that geometric machinery. Or if you believe in positive geometry, then one can do this purely combinatorially. So you can get a basis like so. And these guys tend to form a nice basis for various other spaces. And they seem to be the nice basis for various kind of pairings that Thomas briefly mentioned in his talk yesterday. And for one instance, this is what's called a top part of the Awamoto complex, where I'm looking at the Euler orthogonal algebra modulo some generic one form times the 1 degree less, and that also has a basis given by topes bounded with respect to any fixed element among my ground set, and so forth. And right now we're finishing up trying to write down a nice formula for what happens when I multiply two basis elements with respect to this basis. Can I understand the multiplication constants in some nice geometric way? Think so, but there's There's things a lot more to be checked, so we don't quite have that yet. But in any case, this was, if you like hyperplane arrangements, this is quite pleasing that all the positive geometry picture carries over to oriented matroids in a, with no kind of big hurdles. Or if you like positive geometries, but not necessarily hyperplane arrangement, there are many other varieties, not even just featured in here, that are positive geometries. And one can try to run a similar program where you can either try to look at some nice boundary behavior, or, well, the canonical forms must tell me something about the cohomology. In the hyperplane arrangement case, it's the nicest scenario. In other case, what would happen? I don't know. So I think there's much to be explored, even for purely mathematical purposes. And I hope many of those things might start in this conference. And with that, let me end here.
Okay, thank you very much. Time for questions.
A while ago, we had a paper with Gord and Isabella Novik. You remember?
Yes.
Syzygies of rated Matroids. It goes like, so where we calculated syzygies of semi-reasoner ideal. And it looks like exactly the same combinatorics was there.
Resolution of the standard reasoner.
Yeah, it might be nice to look at.
Yeah, might be, so, but seems to be we have also constructed bases given basically by the same boundary regions and so on. So probably it's kind of a parallel to the story, or might be exactly.
Interpret this as a cellular resolution.
Oh, maybe, yeah.
Okay, others, yes.
You got interesting period values,
Interesting, sorry.
period values?
Interesting period.
Values. Probably, but I have not thought about that at all. Yeah.
Are the constants like non-negative for these omegas?
I like multiply them or?
Yeah.
Well, there's always signs, which are always so hard to get correct. But I mean, like the multiplication is anti-commutative, right? So in some sense, like when is the question like when can I guarantee some positive coefficient? I'm not totally sure.
Yes.
So even in the realizable case, the single element extensions are more general than just a sphere, right? They could itself be non-realizable. And that with zones of Altaire's, right? This bond rest theorem.
Yeah. So even if I begin
With the realizable oriented matrix, yes, yeah.
Does looking at zones of Altaire's help with your
If I look at all tilings, yeah, can I, for instance, like at least carry this proof through in some way?
I don't know. Maybe.
Yeah, I mean, for me, as soon as I noticed this, I was like, okay, maybe I'll try a different method first and then come back to it.
Residue that is special then on these topes. Does it have like a traditional interpretation? So you introduced this notion of residue, as I understand.
So residue.
Is it also like a differential or?
This part?
Yes.
So on the old installment,
It's literally just taking, for instance, if I one wedge, two wedge, it will just go to this. And what is that geometrically? Well, it is the residue map in the geometric case if this did come from a realizable matroid, in the sense that I'm looking at D-log forms of some ratios of linear forms and taking residue of that along a particular function of the form Li over Lj.
or like, I mean, it's the usual residue in the realizable case.
Okay.
So if you change the L infinity,
That's right. Yeah.
do the entries in the like change of basis matrix have some meaning?
Oh, that's a great question. And
I did think a bit about this. Oh, but yeah, I don't remember. Yeah. Presumably there's something interesting as I travel along these general extensions, how the change of basis matrix will be. Yeah. But I don't have a good answer.
number of tokes with respect to one additional general extension is always the
What's called a Mobius invariant, and that will stay the same. Yeah, as long as I have a general extension as the hyperplane infinity. If it's not general, then yeah, of course it can decrease.
as we saw in some sense that talk was identifying where exactly that
happens for a particular kind of array.
If you consider dual, then what happens?
if I consider the dual of the oriented matroid. It can possibly be somewhat messy. Yeah. Because lots of a dual of a matroid doesn't behave as predictably as one would like. And it's also the covectors of a dual oriented won't behave
as nicely as one would like. Other than some orthogonality pairing, yeah, I don't know if.
So if you look at the, instead of cohomology, look at homology of the complement. So that makes sense if you look at the integrals, like given by, for example, amplitudes calculated given by integrals, products of linear forms. So you have to fix some generic parameters and you go around the hyperplanes. That connection, then we can actually ask about the basis in the homology. So there is one basis given also by bounded regions.
Yeah.
I'm wondering if this basis is somehow kind of dual to this basis of canonical forms.
I think
To duality, which I'm not 100% sure the statement one I think you're referring to is this, but I don't know if I got the dual or not. Yeah. Sure. Yeah.
Related to this.
Okay, how about last one for Nick, and then we go over section.
Hi. Yeah, so about positivity of taking a wedge, some wedge product, there's at least for M0N, there's a cool way to generate wedge products which are linear combinations of basis elements, with all +1 coefficients. So that's kind of cool, and yeah, they're related to some non-planar on-shell diagrams. So yeah, maybe there's some original story. Yeah.
Okay, thank you very much to Chris and all speakers.